Hi, I'm Mark Boss, and in this video I will present Neural-PIL, Neural Pre-Integrated Lighting for Reflectance Decomposition. The goal of this work is to create relightable 3D assets from unconstrained image collections. In other words, given a sample image collection, as shown here on the left, we aim to estimate both shape and material properties resulting in a relightable 3D asset as shown on the right. We achieve this by constructing a neural reflectance volume. This means we encode at a continuous 3D location the BRDF and shape in form of density in a coordinate-based MLP. We can also derive the normal from the density's gradient. Due to the explicit decomposition, relighting under even unseen illuminations is easily possible. Decomposing a collection of images faces two main challenges. On the one hand, the rendering of BRDF under illumination is expensive, as one must integrate all incoming lights on the hemisphere. In traditional rendering, this is done by Monte Carlo integration over many samples. As this step needs to be performed during training, the integration needs to be fast and provide a smooth gradient. The second challenge is the ambiguity of the solution space, as for example, dark spots can either appear due to self-shadowing, a dark texture, or dark illumination. Methods such as NeRF or PhiSG also leverage these neural reflectance fields. However, both methods rely on Spherical Gaussian illumination model. One downside of Spherical Gaussians is that a trade-off between detail and rendering speed is required, and that the reconstruction quality is still limited by the isotropic Spherical Gaussians. In the end, the rendering speed is increased by more than an order of magnitude, but the illumination still has visible separate spherical light sources from the Spherical Gaussians. In real-time rendering, this problem is also well known, and especially for specular materials, pre-integrated lighting is used. Here we show the technique from Unreal Engine, where the material properties are decoupled from the illumination Li, and the illumination is pre-integrated and parameterized by the roughness BR. The entire rendering formulation is now only based on a simple set of addition and multiplications. For better understanding, we visualize the technique in 2D. Let's take this exemplary environment map and define how our pre-integration should work. First, the entire illumination sampling should only be dependent on a single sampling direction. However, if we only sample a single way, we need to pre-integrate the environment. This is done based on the surface roughness. A rougher surface equals a wider distribution of reflected weights towards the environment, resulting in a blurrier representation on the object. In real-time rendering, this step is brute force computed in an offline manner, but then enables fast rendering with only a single query direction. We want to replace this brute force pre-integration with a general network called Neural-PIL. Given an embedding which describes illumination, we first sample the direction. Our main network is inspired by Pygarn and film siren layers, which condition our network based on the embedding. In the last step, we apply an additional conditioning network, which defines the integration area based on the surface as shown before in the visualization. Compared with rendering 1 million samples, our method is 2 orders of magnitude faster than a comparable quality Spherical Gaussian rendering. Our method is not only faster, but produces more accurate reflection with even fewer parameters to optimize. Our second contribution is the introduction of priors in the optimization process. We found that by simply training auto-encoders, the lattice space is not smooth, which can lead to local minima. This is especially useful if only parts of a network are used with frozen weights in another network's training. We enforce the smooth manifold by explicitly interpolating between embeddings during training and defining a set of losses which ensure smoothness between the endpoints. Further details for these losses are available in the paper. Here we applied a specific BRDF to each corner and to interpolate the lattice space in between. Notice how smooth our lattice space is compared to without the losses. We now show some results. Notice the plausible reconstruction and relighting under unseen illumination from our method. Notice how our method captures more details compared to NeRF, and nearly as much as NeRF. We additionally capture less floating artifacts compared to NeRF. Overall, our BRDF estimation produces more accurate results compared to previous methods which also decompose BRDFs under unknown illumination. On the left, we also show our performance on view synthesis. On the right, we evaluate on a joint view synthesis and relighting task, as in these datasets each image is taken under different illuminations. Summing up, we replace parts of rendering with a pre-trained general network. The resulting rendering is faster compared to previous spherical Gaussian solutions and provide more detailed illumination. Additionally, our deep priors constrain the solution space and aid in the improved BRDF estimation. Thank you and visit our project page.